my talk is about complex Langevin dynamics in large and gauge theories. First, let me thank Robert and other organizations for giving me the opportunity to talk. And I guess it was a very nice conference for everybody. So thank you all for coming. First thing to notice is that unfortunately this is an older talk. So my affiliation here is wrong. I'm a faculty in WITS now, not in India anymore. So please ignore that. Okay. So I'm talking about complex Langevin dynamics and large and gauge theories. So let me give you a little preview of what I'm going to talk about today really. So basically, one of my interest and interest of many people in physics is to understand matter at finite density. So it has thousands of applications. I'm not going to cover all of them. And mostly what is relevant for high energy physicists is something like a quantum gauge theory, like for example QC, a prime example of a gauge theory which occurs in nature. And the question people would ask you often is that what happens when you put a QC-like system in finite temperature and chemical potential operation? That's a very involved question and very interesting question. Although I'm not really going to talk about it at all in this talk, but let me give you some kind of explanation for this plot, so that physics, that what are the possible physics of, I'll give you a simple example, explanation, not all the details, but roughly what are the physics which one may expect and what is going on, to give you an idea that one of the most interesting things. So you see that what happens, so if you take a, just for the students here, so if you take a theory like QCD, what it has gauge field and flavors. Now suppose it is believed that if you get rid of the flavors and look at the pure gauge theory and heat up the pure gauge theory from zero temperature or from a low temperature, what happens is that the gauge theory goes through what is known as a deep confinement transition. Okay, and in the era of ADS-CFT and in talk of string theory, you would always ask that what is the holographic correspondence, holographic dual of everything I'm talking about. So holographic dual of this kind of transition, this deconfinement transition, is believed to be Hawking-Page transition. That is a transition between black hole and empty ATS. So this occurs in various different scenarios. Some are called, not called Hawking-Page transition, for example, Witten's work in ATS soliton and those kind of things. But the idea is that there is a black hole solution with horizon and no black hole solution. And the black hole solution with horizon corresponds somehow to the deconfined phase, is at the frequency of order n square, and a transition, a phase transition between black hole and no horizon solution is akin to the deconfined and deconfinement transition in QCD. Now, what happens when you have flavor in QCD is that, or QCD is a complicated thing. Take the name more generically. So in this kind of gauge theory, if you end up having flavors, what it does is that it somehow make this, it is believed again that if you have sufficient number of flavors, often that dissolves the transition. Means you won't anymore get a confinement-deconfinement transition. Often you get a steady crossover between deconfinement and confined phase, etc. Okay, so this is along this temperature. This is, and if you turn on the chemical potential, what happens is that then you see various kind of condensation forming. First is that you transit to a state called nuclear matter. Then there have to be other superfluid, conducting type of transition where various operator like two pair of side-side condensate, they pass the baryon condensates in some ways. So baryon number have non-zero expectation value, so it goes through various kind of phase transition. And it is believed that these phase transitions often are first order phase transitions. So rough picture is like this, it's complicated. Now what happens is that so before going into what I'm going to talk about, so first let me emphasize the simple fact that you may ask that what happens, as I've just told you that okay, if you take a pure quantum gauge theory, a confining gauge theory, you have a deconfinement transition, and if you introduce flavors, this deconfinement transition is no more there. And people believe that the real world QCD is more like that, but whatever. You may ask that what is the holographic dual of it? So if you take a holographic theory and introduce enough number of flavors by introducing say D branes or something like that, is it true that what happens to the confinement deconfinement transition? So this is not a very well studied question. It is numerically very hard to do. I'm not going to talk about it. So what happens is that in holography, as we know, that the black hole has a mass of n square, order n square. N is the number of colors in the dual gauge theory. So if you want to change this phase transition significantly, you have to introduce a lot of flavors. That is, flavors will be of the order, same order of n. Nf number of flavors should be of the same order of n. And this flavor should have a back reaction. And it is still not known how these back reactions change the phase transition of the black holes. But just to give you an idea of what may happen, is that, for example, in the left, I have here I have given just a ATS to pure black hole transition and Hawking page kind of transition. You will take empty ATS, increase the temperature, there is a first order transition and you form a black hole. So, interestingly, what happens if you have flavor is something pictorially one can think, although it is very difficult to do these numerics properly. But pictorially what happens is that having flavor means having some brains inside the ATS. What kind of brain, etc. This is a more involved question. But let's just think that it's just a line inside this ADS which looks like a sphere. ADS is like a box or a compact sphere. This is the boundary of ADS. And once now if you put on temperature in the system, what happens is this, as you have brains, something to catch the energy. So you basically form a little black brain inside the ADS. Rather than a theory of gravitons, means that carbon gravitons, you form a little black brain. Means that which is little bulged in the middle because of the redshift factor. And then there is a big black hole. What happens is that if you have enough number of brain, the bulge becomes so big that there is no clear transition from this bulge to a bigger black hole. It continuously turns into the big black hole. So that way possibly the deconfinement transition get dissolved. Now, one can do similar studies in free gauge theories. So you can look at the free gauge theories, large N gauge theories and boundary, integrate out various modes and look at effective action, which I will discuss in a minute. And in that free theory, if you introduce flavors, exactly the same thing happens. That you will see that at the beginning there is a transition from some kind of ADS-like vacuum to a black hole vacuum. And then what happens is that this transition gets dissolved as you have enough number of flavors. But that all in the temperature axis. But today I am more interested in the chemical potential axis of this first figure. Not the first figure as well, but generically in a large N gauge theory. Okay, so what is the main problem of having a chemical potential? So this will be a little bit mysterious because I have jumped some steps. I will explain what I have wrote in this thing. Is that if you have chemical potential, and that's a simple but interesting point to note, is that when you solve like a theory like QCD, etc., or any other theory numerically, what you do, you put it on the lattice. And when you put it on the lattice or do any other kind of simulation, first you analytically continue the theory to an Euclidean theory, then you try to solve the theory in computer, if you are doing it numerically. Because these are mostly strongly coupled theories and there is no known, well-accepted analytic method to solve it. Now, if you have chemical potential and you analytically continue the theory to the Euclidean time, the chemical potential term becomes complex. Because chemical potential term is like mu into Q. Q is charge. Charge generally is a current, which is one derivative of time of it. Even if it is free scalar, doing nothing complicated. If it is one derivative of time, we analytically continue it. It becomes I into the derivative t to I tau. This derivative also picks up an I. So analytic continuation of a theory with chemical potential is often leads to complex action. And if the action is complex, this happens for a free scalar theory. For example, a very simple problem in free scalar theory is that you take a free scalar theory, a particle in a box or something like that, nothing more complicated than that, and you put it on a lattice and put finite chemical potential. If I ask you to, okay, we all know that there will be Basu condensation, right? If you turn on chemical potential sufficiently high, there will be condensation of the scalar field. So this is called Basu condensation. A free scalar, no interaction, nothing. That simple problem itself is not so easy to solve numerically. Once you have chemical potential, the action will become complex. And complex action, what is the problem with simulating complex action? So when you numerically solve, the problem with complex action is that complex action is that complex action is that this action has a real part. Sorry, can we write? As this SF, this as you can see, this is not a positive definite quantity because it fluctuates. And if it is not a positive definite quantity, it's difficult to solve numerically. For example, this integral, if you want to solve numerically, it's very easy to solve because you can solve it by maximal sampling. Most of the contribution is coming from here. But if I change this integral to something like this, then this integral so looks like this, with even the real imaginary both of the parts, and somehow the contribution comes from the cancellation of peaks and dips. And so any kind of generally solved, numerically solved things by maximal sampling. And if we are not matching the peaks and dips properly, this integral is very difficult to calculate numerically. Almost impossible if you are using standard numerical techniques like Monte Carlo, etc. Because it's fluctuating. The same happens if you have some complex part of the action. This is not a very converging thing. Things are widely fluctuating. It becomes almost impossible to solve. Okay. So what are the way out? There are a few methods over the last few decades which has been proposed by various group of people, etc., like Vegas, collaborator, various people, Saylor. And so one method to solve this kind of things is by what is known as complex Langevin dynamics. There are other ways, more logical ways to look at various kind of deformation of contour, etc., which the ellipses can go, that I'm not going to talk about immediately. So what is the idea? of complex Langevin dynamics is very simple. Now, if you want to solve this integral, this can be solved by looking at these dynamics. Okay, so beta is a normal 0-1 noise. Hence, if you want to solve this integral, the idea is that to start solving a stochastic differential equation that is simple, that x dot is equal to whatever the action you have, the derivative of this, plus some noise. Okay, and one can show that a stochastic differential equation, the solutions will be a probability distribution. So at long term, the probability distribution converges to this number, this distribution. So if you start simulating x with this distribution and do it for a very long term, then the probability distribution at the end will actually be this distribution. So basic idea is that you run this simulation and start sampling at the long time, then this sampling will actually give you a good sampling of this distribution. This is called stochastic quantization. Okay. But interestingly, this method, a simple generalization, is there any kind of, it is okay. So Langevin dynamics is that the complex Langevin dynamics is something, what it is that if you have this kind of equation, so then also one can show that if in the complex plane, if you simulate this equation, if you simulate this thing, then the claim is that it's not super easy to prove, but it's sometimes true, sometimes not true, depending on how. But roughly the aim is that if this equation is solved in the complex plane itself, then what happens is that the n distribution will be a two-dimensional distribution in the complex plane. Because this is a complex dynamical equation. So n distribution will be two-dimensional probability distribution in the whole complex plane. Right. But if you have an analytic operator, then this at long time will be t tends to infinity, this Langevin times tend to infinity will give you Tx. So Px here is this fluctuating distribution. Is basically e to the power minus sx. Where s is itself a complex function, so sr plus I sx. So this is a fluctuating complex integral. However, this integral is same as this integral, where pz being a probability distribution is a positive definite function. So this part can be evaluated by maximal sampling. Although direct calculation of this one-dimensional integral by maximal sampling is very hard. But its two-dimensional integral is relatively easy because unlike the one-dimensional probability distribution, this two-dimensional tablet distribution is positive definite. Because this is the end result of this thing. There is no obvious reason that why it should be true. But one can argue that this is, I'm not going into the proof. And it is often not true. These dynamics may not converge, etc. There are other issues with that. So one has to be careful, and nobody yet knows exactly on which condition this kind of dynamics converges, even for a simple system. Okay, so now the idea is that what it is related to is that suppose if I want you to calculate this integral, so often this is done in elementary school or colleges, by deforming the contour. So, and once you deform the contour, so first the integral was defined here. Now you deform the contour along this line, and so here this probability distribution is fluctuating along the right contour. It is actually a peak distribution. Basically, you go to the zero of this function where the saddle point of this integral and accordingly deform the contour. Deformation for this simple thing is a shifting the contour by ID or something like that. Now here this a maximal sampling is possible. This method is called Lipschitz thimble or something. It's a little involved because you need to know the saddle points of these equations, which is not always easy to find. But this complex Langevin dynamics, if you look at this two-dimensional probability distribution, it is often, but not always, actually concentrated around the saddle point of this equation. So you start with here, your complex Langevin dynamics will take you around that saddle point, basically. You are sampling in that region. Okay. So this is known for some time. People are trying very hard to use these things in QCT. It works, it doesn't work, and nobody is sure if it works or not. It's not working, it's a complicated question. So we thought that, okay, let us try to use those methods in some large and gauge theories and see that if they work and what kind of H diagram they gives rise to. And good thing about large and gauge theories, lower dimensional large and gauge theories are solvable. So maybe if we can solve the lower dimensional large and gauge theories and see that this method matches with the analytic results or not, then we can slowly go to higher and higher dimensions, and maybe at least in low enough dimensions these results will be trustable. Now that's the real motivation for it. Okay. Okay, so for example, get into this kind of thing, the first thing I'll tell you that what is the simplest large and gauge theory? The simplest large and gauge theory, which has all the essence of high dimensional QCD, analytical force superangle, but much more simple, is a zero-dimensional matrix model with large and unitary matrix. They are like the gauge, that's the gauge group, SUN. So the simplest matrix model is written here. It is, the action is very simple. It's an 8 raised C plus 8 raised to dagger, and the integral is over is zero-dimensional. Zero-dimensional is just n cross n unitary matrix. There is no spatial, no temporal, nothing. So this is a very simple example of a gauge theory. So we'll discuss in a moment that why this exactly very similar model we can find from various lower dimensional gauge theory. In some cases, it's force superuniverse theory in certain limits. But let's assume that this is the most simple gauge theory. Now, what is the phase of that gauge theory? Okay, so before going to the phase structure, etc., so what happens is that if you, let me discuss that if you take a integral force superinverse theory and things like that, and say weakly coupling is equal to force superinverse theory, and you start integrating out outer nodes, then you are ending up with only the Boliakov loop, and the effective action of the Boliakov loop looks something very similar to that. It is actually exactly not that, it is actually trace you into trace you dagger, but if you have fundamental fields rather than the adjoint field, then you get 8 raised to dagger plus 8, exactly you get 8 raised to plus 8 raised to dagger. And E then becomes the single partition function of that adjoint flavor. If you just have 1, it is just e to the power minus beta m. And if it is on sphere, you have other Fourier modes, etc. 0 plus 1 dimensional gauge theory is just e to the power minus beta into trace u plus trace u dagger. So in from various gauge theories you get this. I'm not going into the derivation, that will take you out of the main context of the talk. But this is an effective action for various kind of nearly free gauge theories with weakly coupling, etc., defined on compact spaces. 8 resu plus 8 resu carrier. And so in large N, this theory can be in various kind of phases. So this theory, as you can see, is a large N theory. So it is an n cross n matrix. It has n eigenvalues, and as it is an unitary matrix, all the eigenvalues lies on the unit circle between 0 and 2 pi, say e to the power I theta, theta from 0 to 2 pi. Right. Now what happens as it is a large N theory, so eigenvalues form a continuum almost, and then you can define the theory by eigenvalue densities. And so this density function can have various kind of interesting properties. So this density function on a sphere, so it is like this open of the sphere from minus pi, sorry, the circle from minus pi to pi. So the density function could be in two phases. One phase is the gapped phase and the other phase is the ungapped phase. So this is known for a long time. So the gapped phase, the ungapped phase, this is like this, and gapped phase it is like this. So if you kind of take a real theory, for example, and take this action by integrating out other modes, then A at low temperature will be very small. The theory by default will be staying in the ungapped phase. As you increase the temperature, the theory will transit into gapped phase. And generally for a more realistic theory, so there will be a third order condition in between when the gap closes and joins. But in more realistic theories, what happens, at least in weak coupling, you will have nonlinear terms, so you actually jump across the gap. You never get the gap closing if you don't have fundamental flavors. You always get a jump across the gap. It will generally be a first order condition. Okay. So now, what happens if you have flavors? So as I've discussed that, and a chemical potential. As I've discussed that once you have chemical potential, the action becomes complex. Again, one can show from if you look at a simple 0 plus 1 dimensional gauge theory, like just with one field phi, nth number of the plus say n square phi square, just a gauge theory like thing, gauge theory in 0 plus 1 dimension, and integrate out this phi mode, then the actions of the Pallab loop will be A beta e to the, so A beta trace u plus A beta trace u there. That will be the action for Pallab loop. Now, if you have chemical potential and where A beta is just e to the power beta m. If you have chemical potential, that changes to e to the power I mu into something, into beta I mu. So this A beta becomes a complex term. So the idea is that then if you have also chemical potential, then A and B are no more the same thing. Sorry, it happens that it is like, it is minus mu and it is beta plus mu. So, sorry. So what happens is that if you have chemical potential, it changes the relative weight between a flavor and anti-flavor. So their relative weight in this action will be different. So that is why A and B are not necessarily the same anymore. And once it is not same, this action is no more real. It is a complex action. So all the same problems comes up. Now, that's an interesting thing. It has been done by people from group. It's one single thing. That if you have this kind of theory, and if you try to solve this theory by ordinary Largen techniques, etc., try to find saddle point distribution, just that I said that the saddle point distribution is a gap, ungapped, etc. If the theory's action is not complex, just like in the simple Gaussian integral, The saddle point actually lives in the complex plane. Here also the saddle point doesn't live on the unit circle anymore. It goes away and lives in the complex plane. So the eigenvalue distributions are, interestingly for this model, is not on the unit circle, but lives away from the unit circle. Like if A is equal to 0.3, beta is equal to 0.15, this is the unit circle, and this is the card where actually eigenvalues live. They do not live in the unit circle anymore. Okay, and then this model is a little difficult to solve, but it still has similar phases, gapped and ungapped phases. And in the complex AB and the contour where where the eigenvalues lies are given by a relatively complex equation, which is given by this equation. So this is a transcendental equation, difficult to solve for R as a function of the radial direction, but you can solve and numerically, and that's where all the eigenvalues would go. This is the contour.
Question. So the parameter you have taken to be complex.
Yes.
But still you are looking at eigenvalue distribution of a unitary matrix, I think.
Right.
So why is it going beyond unit circle?
The thing is that it is true that we are looking at the unitary matrix, but it is generally not true that suppose if you take any integral, forget about the unitary matrix, that it is not guaranteed that the saddle point of the integral will lie in the contour you are looking at. That's not true even for the Gaussian integral. If you a minus x square plus I bx, the saddle, if you integrate from minus infinity to infinity, the saddle point lies outside the contour. So you have to define the contour to the complex plane. So here it is an infinite dimensional integral over various thetas. And all the thetas by the integral contour is that all the thetas are real. Right? Right. And then my claim is that that's not the contour where the saddle point of the integral lies. Saddle point of the integral lies in a contour where thetas are not real. So that is why this eigenvalue distribution is going away in the plane. Okay, so this is the distribution of eigenvalues in the gapped and ungapped phase. So this is the ungapped phase and this is the gapped phase. And so basically if both A and B is equal, the gapped and ungapped condition happens both is like 1 or something. Here if 1 is 0, it happens at 1 by E. And then there is a line like that which defines the boundary between two phases. And they are thought of as these things. So these results can be very validated. So our first goal was that if you use complex Langevin dynamics, can you reproduce this result? Numerically. So we solve. So this is the overlap of numeric result and analytic result. So we see that our numeric result and our analytic result has nice matching. And what we did is that, as I just discussed, that we just follow the procedure of complex Langevin dynamics and solve z dot is equal to minus del z s plus some noise term. Noise is the order of the noise is 1. And one can show that y is the same, etc. It's like that. So I'll just, for a visual demonstration, I'll show you a video of how it looks, that how this is the complex progress of complex Langevin dynamics, and you start with the unitary matrix, all the things on the 0-1 circle, then it goes to a gap phase, and the gap open up. So, and this is possibly another one. This is an example where it remains in the ungapped phase, but still goes away from the unit circle. Yeah, so we looked at various things like various change of parameters, etc., increase the size of the matrices, various things. So this is performed by my collaborators in India. I won't go into that. And various other quantities which we calculate from like fugacity, the eigenvalues, the expectation of trace, dagger, etc. also shows a good match with analytic and numerical results. And we can look at more complex matrices. For example, we can look at one dimension or the free theory in multiple dimension, and even for those theories, we get a good match between analytic and numerical results. Okay, and so we also did look at the cases where there is no analytic solution available. Suppose if you take, if you introduce a coupling, even for a 0 plus 1 dimensional theory, if the coupling is strong, it is not easy to get what exactly the effective action for trace dagger. And in those theories also, we have seen that this thing, now what is the conclusion is difficult to say, but we can see that increasing chemical potential can increase the chemical potential, and that apparently gives meaningful results in the sense that we see signature of post-condensation, and we also see various things like tracing, for example, the gap opening transition, etc. for 0 plus 1 dimensional theory. So we are still studying some aspect of 0 plus 1 dimensional theory and how exactly the post-condensation realized in this thing. And we believe that post-condensation, what happens near the post-condensation is that when the contours breaks into two contours or something like that, but we are not yet 100% sure how to numerically get it, etc. So this is roughly the status of this will be for various values matching, etc. And if you have really take a theory on S3, a free gauge theory on S3, and turn on chemical potential, so it goes through various kind of gap opening transition. So first the gap actually opens up as we increase the chemical potential, but if you increase the chemical potential more and more, the gap actually closes at some point. Basically, theory is symmetric on the theta going to z going to 1 by z in the theta plane, and that changes from mu to 1 by mu to some ln mu to minus ln mu or something like that. So as we increase this parameter, the phases of the theory repeats itself. For example, this phase is very similar to that phase. This phase is very similar to this phase, where we transfer z to 1 by z. So, and this phase is actually so like that, and this is similar to this once we do the z going 1 by z transition. In that way, so we can get this thing numerically, etc. And also, most interestingly, things tends to match for 0 plus 1 dimensional, non-dimensional theories. So this is still an ongoing work. There are a few various questions that can we get 1 by n effects, and does 1 by n effect near third order transition match? Can we get even a numerical results? And that will show the strength of the numerics. So we have looked at various interactions. Now we have also looked at 0 plus 1 dimensional theory. I am still working, this part is we have done, and we just looked at the result. And we need some higher dimensional, it's a little bit complicated, we need gauge cooling, etc. And we are still exploring those things. So this is, thank you.
Yes, so there's time for questions.
I've got a question. So the thesis seems to be a very important part of this, but I wasn't quite sure. I probably missed it. Like where did it come into action or whatever, so that you eventually got the gaps and gap, which was there.
Okay.
I just want to know how the theta, how you got the gaps and maybe that's it.
Sure. Yeah, so the thing is that suppose if you had any matrix model, say like this is the action set.
Okay, so it's just infinitely small parameter.
Okay, and if n is large, then you may expect that in a larger limit one can argue that, and there is a n there. So in the larger limit, all the contributions are coming from one saddle point. One saddle point means that one snapshot of u, and one snapshot of u is somehow determined whether the gauge transition is by the eigenvalues. So it is the question, so we have n eigenvalues, all lies between 0, so they all lie on the circle, and in its circle it is a I theta because it's a unitary matrix, so you can say that some number between 0 and 1. So as there are n large number of numbers, so they are like very conservative. So you may ask that what is their distribution? So you have a distribution like this. So this distribution goes from here and comes back here. But at some kind of parameter, if A is large enough, the distribution will be more like this. So it suddenly becomes 0 at some point. That's the gap of it. Okay, that's really true at strictly at very large end. If n is not large, so there's some kind of tail to that distribution. And this tail indicates in certain ways also. So some power loss in some cases. But for strictly large end, you can have this gap.
Anton, you have a question?
Yes, so this is 0 plus 1. Can you do 1 this is just an integral. So can you do the one-dimensional mechanics? Which is also has similar close written linear transition.
Yes, if one dimension, so suppose you just take a 0 plus 1 dimensional gauge theory. And the simple example is that you have a scalar field and the scalar field has mass. And in this theory, you will actually get a cross-written Fourier kind of transition. That's the claim. That is not something which is exactly solvable. In a way that even for the field theory, if you integrate out, simplification, actually the action will not be this, but will be this, right? Is like e to the power minus beta mu trace to the power minus beta intrinsic dagger. And then there is a summation of n.
Right.
So this is like n is 1 to infinity. So this is actually is more complex. However, it seems that even for these theories, you generally have a transition like this. What happens is that higher order terms are generally, if these terms has thermal origin, because if they are of the form beta Nm, then higher order terms are sufficiently small in general. And you just would have a first order transition kind of thing. Not first order, it's third order transition kind of thing. But things changes considerably if you have an interaction. What happens is that if you integrate out the interaction term, even a small coupling, you get terms like ratio, dagger, square. And these terms somehow let you jump over the third order transition often. So it is not that things gradually opens, because this term, the effect is that you jump over the third order transition point. One can discuss that, but sometimes it happens. So it's a little more complicated if you have interaction. But we did few simulation, at least for some region of parameters, there are this kind of condition. The simulations are difficult to do because, as you said, that in 0 dimension is easy because it's just actually it is not a n cross n problem, it's n dimensional problem. But in 1 dimension, it is really n cross n problem, also do simulations. So,
Okay. Any other questions? All right, so then let's thank Pallab again.